All right, good morning. So lab 2 will be less frustrating than lab 1. So the unit of frustration is 1 physics. So lab 2 was about 0.7 physics, lab 1 will be about 1.4 physics. Chemistry is about 1.7 physics. And I still want to say one last word about the meaning of potential energy, because I feel like some people not really have a grasp what is it. And I'd like to start from a question. What is the name of this object? How do you know? How do you know the name of this object is a table? How do you know? Well, you moved. Too late? No. What experience? Just the second you were born, you knew.
Like we learn from the people, like there's common definition.
So you've been told, that's it, nothing else. Someone, not us, a long time ago has invented this word, and it's been commonly accepted, and it has become a definition, nothing else. That's what a definition is. And a definition of potential energy is a little bit more complicated than just a definition of a table. And that's probably why some people still may feel confusing about it. But basically, it is just a definition. When we study the nature, first thing we see the presence of objects, something happening to them, and then we arrive, thank you, Newton, with the concept of a force. And then we will learn there are many, many forces. We study property of those forces, and basically every force is just a reason for acceleration. That's what we know. And then, for whatever reasons which don't matter, in science reasons don't matter, we come up with a new definition, work. And for a constant force, that was the definition. And the definition is, we've been told to call this work. That's it. And then we started calculating work done by many, many, many different forces. And turns out, for some of those forces, no matter what experiment we run, we always come up with a combination of variables such that if we subtract final value of those variables from initial, we get the work done. And if it happens again and again and again and again and again, we say, oh, probably we should call it. Probably we should give it a name. And we give it a name, potential energy. That's it. That's a definition. Now, potential energy of what? Here people still have a discussion at potential energy of an object, of a force, of a system, of a field. Doesn't really matter at this point, as long as work can be calculated as a difference between initial and final value of something. That thing is potential energy. Now a question. Please just read the problem and don't think about it. Start drawing a picture. because the answer is in the picture. And so we can calculate many different things in this problem. But first question for you is about the direction. That's the direction of electric field. And of course, if we are searching for the answer related to direction, we have to connect it to some direction which is presented, given to us. And well, when we read the text of a problem, we start making a translation from, well, in this case, English language into a symbolic language and pictorial language. There are many different languages. And the first languages actually didn't use any words. They used pictures. And now we have forgotten this skill. So we have to regain it. And the charge initially is not moving. But when we turned on the electric field, well, we don't know yet anything about it except it's there. And the charge now is moving to the right. How do we know? We know words. So now you have to select from the list of equations what one equation should you use to relate the direction of electric field and there's only one direction presented here in addition to the question is velocity or displacement. So you search through the equation sheet, which everybody should have printed out already. And you don't see that in equation. It doesn't exist. So you have to start searching for something else which might eventually connect what we know, velocity, and what we're looking for, direction of electric field. So by now, the majority should have answered already something. That is the question number 2, which is where? Here. Okay. So if we cannot find an equation which directly relates what we know and what we're looking for, in that case, we just start searching for equations which relate what we're looking for with something, or what we know with something. So it's like we need to build a bridge. All right, and we can start it from both ways. Electric field, it is related to a charge but also related to a force. It is related to a distance, depending on how you look at it. Velocity. Velocity is related to displacement. Well, in this situation, we can just look at one axis. It is also related to time. It also might be related to acceleration. Still not connected. So, but now we have clues, because if we keep searching for connections, there is a connection right here, which we recently refreshed when we talked about forces and potential energy. These two variables are related, connected. And now we can see that, yes, we can connect directly electric field and velocity. And this connection should go through force. So we start writing equations. And the expression which relates force and acceleration. Now an expression which relates acceleration and velocity. Now the initial velocity is 0. So if we look at the very last expression, it tells us immediately tells us that if velocity points to the right, acceleration also points to the right. Now if we go to the next equation, if acceleration points to the right, that means force points to the right. Now if the force points to the right, that means what? Does it mean acceleration always points to the right? I mean, the electric field always points to the right? If the force points to the right? No, because there is another variable, Q, and the difference between Q and M is the mass, never negative. Q is a charge, can be negative, can be positive. So we don't really know until we read. And if it is positive, in that case, yes, electric field points in the direction of a force. However, if the charge would have been negative, electric field would have been directed opposite. And, well, we have answered this question. Okay. If we want to solve this problem, I need to add an extra slide. Let's add an extra slide. So now we actually have, what happened here? Okay. Now we have a specific strategy which, if we want to, we can use to answer the question about speed. We just have to do it backwards. We can calculate force, and then we can calculate acceleration, and then we can calculate speed. Well, so there is also another approach. Just as an exercise, we can use it using energy, because that was the last topic, energy. So the object travels from here to there. The initial speed is 0. The final speed is what we are looking for. Now, the distance traveled is 10 centimeters. Okay. And it travels because electric force acts on it. Okay. Now, we know in terms of energy, change in the kinetic energy should be equal to the network. In this situation, that's the only work done by electric field, which is supposed to be equal to charge times initial potential minus final potential. But we already know it's speeding up. So, and the charge is positive, so we can just write it like this, using absolute value of potential change. Now, you may be confused right now by letters, because V represents speed, V represents potential, and also V represents volts, unit of potential, so you have to keep track of all those letters. But if we are looking for speed, well, we have to calculate final kinetic energy, because initial is 0. Kinetic final minus 0 is equal to charge times potential difference. And that is equal to mv final squared over 2. And we know mass. So to calculate final speed, we need to do what? We need to do this 2 times charge times potential difference divided by the mass and the square root of that. Well, the only thing we don't know yet is potential difference. But now we can search for a connection between potential difference, electric field strength, and the distance between 2 points on electric field line. So we always search first for the existence of a connection. We need to know very well what is connected to what. Yeah. This is what, and then we can ask a question. How? Those are different questions. To answer the question how, we can write an equation. An equation says the magnitude of the strength of the electric field equals the ratio. But in this case, you just have to use it backwards. Yeah. We can solve it for the potential difference, and that gives the equation for the final speed. And of course, if we would use Newton's law and kinematical relationship between speed and acceleration, we would get the same result. At this point, we need to just what? Okay. 2 times 2 nanocoulombs times 100 volt over meter times distance 10 centimeters 0.1 divided by the mass 10 grams, right? I suspect it will be 2 times 10 to wherever. Let's see what wherever is. Actually, no. No luck. No. Square root of 4 is 2. Now, you have to count with me, -1. So 10 to -9, -10, and 447. You have a calculator, so you have to calculate it. And tell me, yes? On the exam, you will have the equation sheet, and by your question, I assume you haven't printed it yet. So, print it out, look it up. Well, we talk about capacitors and specifically parallel plate capacitor, when we have two large plates or small plates parallel to each other and charged, maybe with a dielectric inside it. So the next question is how to calculate capacitance if we know everything. So what we have here, two plates, and there is a material inside, and this variable dielectric constant describes the property of that material. By the way, this is again a rare situation when a physical quantity has no unit. It's just a number, 3. And all we have to do now is just plug numbers in. So 3 times 8.85 times 10 to the negative 12 times area over distance. So we assume that wax fills up completely the space between the plates, so the distance between the plates is equal to the thickness of this material, which is 1 centimeter, and 1 centimeter we need to convert into meters, so 1 be divided by 100.01. Now, area, 320 centimeters squared. Well, we just said 1 centimeter equals 1/100th of a meter, and we have to square it, and that's it. The result will be in such unit we call farads, and people use 2 different letters for that, just capital F or a Greek letter phi, farads. Okay, please calculate. So I'm going to round it up. 3 times 9 times 10 to the negative 12 times 320 times that's going to be 0.01, because in my mind I cancel 0.01 here and 0.01 there. Just to write it clearer. And now you have to take a calculator and calculate. And I'm going to start calculating what? Calculating the charge. Again, very straightforward calculation. To calculate the charge, we just have to multiply 2 numbers. The capacitance, well, before you tell me the number, I'm just going to write times the potential difference between the plates. So whatever number you will tell me for capacitance, for the charge, you just have to be same number with the shifted power. So what is the capacitance equal to? Times 9 times 3.2 Anyone, please. Yes.
8.5 to the 10 to the negative 11.
Okay, thank you. If that is the wrong number, that's her fault. Mhm. This is how most commonly people would write it down. There is a common set of prefixes, nano, micro, pico, or pico. So now we just have to multiply by 100, and that's going to be 8.5 times 10 to the negative 9 coulombs, or 8.5 nanocoulombs. Most problems like this are very straightforward, but we will be using this in the future for more complicated calculations. So most work done here on conversion. Yeah. Question? What do you think? You see a letter. It is the same letter. Does it have the same meaning? Well, of course, the answer is provided by the understanding of how an equation works. For example, the Coulomb's law, it says you need to have two charges, and R represents a specific distance. And the second equation says you need to have a charge, and R represents a specific distance. And you have to say out loud or in your mind what it means. So in a Coulomb's law, R represents the distance between two charges. In a second equation on the right, for the strength of electric field, R represents a distance from a charge to a point in a space. So does it sound the same? No? They are different. People sometimes confuse the meaning and the letter. Next question. What do you think about this situation? Well, two questions. Two questions. Again, about terminology, because terminology represents the language. If we use it correctly, most problems can be solved with the least risk to make a mistake. But if we start using terminology in our own way, the risk to make a mistake is much higher. And this is something you may not know, so just feel your gut feeling. Yeah. This you should know. And just think about it. Potential difference, according to a definition, is the positive number which always represents what? The magnitude of a difference between a potential number 1 and potential number 2. Two potentials. Between two potentials. So if we have an electric field, we need to have two different locations, 2 points, P1, P2, in that field to measure potential number 1 at one point, potential number 2 at another point, and then we can calculate the difference. And then that's what you read on any device, 120 volts. This potential difference also has a different name. That's exactly the same thing. If you read this word, voltage, that means potential difference. That means absolute value of actual difference between two numbers. But this term, electric potential, represents something happening at one single point. Here, electric potential here. But as we just said, the word voltage represents something related to a pair of points. So electric potential and voltage cannot be used interchangeably. Those are different things. It's very important to remember, especially for the lab. All right, now I advise you to find some time later at home, just play with this applet. You can download it, you can see lots of important and interesting things, what is happening. So this is a model of a parallel plate capacitor, and it's connected to a battery. Well, we just have to charge it, and now we can see what is happening when we connect a battery to a capacitor. It just starts acting like a pump. We cannot create electrons. We cannot destroy electrons. We can only make them move. That's it. So how? Well, we have to give them the room. If I would use a plastic wire, nothing would work. I have to use a metallic, conductive wire. But also, we have to apply potential difference, which creates electric field, which creates a force acting on electrons, and they start move. How? Well, in this situation, so this battery has a positive terminal plus in the middle, negative here, which means the plate connected to a positive terminal will have a higher potential, and this will have a lower potential. Normally, we just set it to 0. If this is set to 0, this will be equal to 1.5, no, 9, no, 6 volts. So right now, the potential difference, or now we can say voltage between these two plates equals 6 volts. Also, what's happening? Well, electrons now begin moving. They cannot jump across. It's impossible for them. But now they have a path. So how do they run? Well, if this plate should become positive, it has to lose electrons. So electrons start running and being collected here. That's it. And when everything stops, equilibrium is reached, the number of electrons this plate gains is equal to the number of electrons this plate loses. The law of conservation of charge, which means this plate will have the charge same magnitude but opposite to this. And we actually can calculate, if we measure the area, distance, and for the air, dielectric constant is 1, practically 1. We can calculate the capacitance of this capacitor like we did. We can calculate how much charge do we store. And we can start asking questions, what's going to happen with the charge if we make plates closer or further, or if we, all right, it's not too humid so I can keep everything here, hopefully. What's going to happen if I increase the area? And by increasing area, I mean just touching with additional conductor, more area. How does it affect? So this applet helps to answer all those questions. Now, electrons move. Moving means kinetic energy. So this battery, to charge the capacitor, has to do some work. And in the end, the capacitor has some amount of energy stored in it. So how do we calculate that amount of energy? Well, we can imagine initially, there is no charge now, nowhere. So first I have to take one electron and physically move it. But as we know, the amount of work done by electric field doesn't depend on the trajectory, on how long the path is. It only depends on the initial and final potentials. So I can move it like this, or I can imagine I just move it directly. Doesn't matter. Same work. So first time there is no electric field. First electron travels without any work done. But now when it's here, well, I'm sorry. Electrons are blue. When this electron sitting here, second electron already being repulsed by this. But when we have two electrons, they will repulse it. Even stronger, the third. So every next electron has some more work to do. But we can just calculate the work using the same equation. Charge time potential difference. We just have to calculate, use the average one, the average between 0 and the maximum. And that finally gives an equation for the energy of a charged capacitor. This is that actual potential difference, actual voltage, which the battery provides. There is an electric potential here, normally set to 0. Electric potential here, 6 volts. Potential difference between, and people say the voltage across. That's the language. The voltage across this device, across the capacitor. Well, now we can calculate the energy inside every capacitor, but that's not the only one equation we can use for that. Because, for example, we can replace the charge with the product of capacitance and voltage. And that gives an equation which sometimes is very convenient to use when we don't care about charge or don't know about anything about the charge. Or another variable which can be replaced is voltage. Strictly speaking, we have to keep in mind that all those variables are positive. So, and now, if I replace the voltage with the ratio of charge over capacitance, I've got one more equation which also tells us how to calculate the energy of a capacitor. So you all have an option. You can memorize all three, or you can always derive quickly, and the equation sheet has this equation on it. Yeah. So you can use either. It's just a matter of convenience. They're all equally correct. So let's just as an example calculate quickly the energy stored in our capacitor. So I have to go back in time to check the numbers. So for example, the charge and capacitance, no, I like voltage because it's just 100. So charge and voltage, that's what I want to use because it's easier for me to remember. Charge and voltage. Charge and voltage, so I'm going to use, oops, the original equation, 1/2 charge, 8.5 nano coulombs. The voltage is 100 volts. So what does it give us? 4.25 -7 joules. I don't want coulombs here. Usually I don't write any newtons if I assume international system of units. So also pretty straightforward usually. Question: what do you think will happen? So let me show you. So what is happening? First of all, I want to discharge the capacitor. So wherever I had the extra electrons here, now they moved back, it's neutral. So I connect a battery to this capacitor, and I know that the capacitor immediately becomes, almost immediately becomes charged to a certain value. Then I disconnect the battery. And then what do? Increase in area. Well, what can I do? I could move the plates, but in this particular situation, I'm increasing the area. That's it. And the question is, how would electrons move? So now you got to choose your answer. And actually, let's say, disconnect the battery, and now we can enlarge the area. All right. And survey says that the question number 6. $27 is not enough. Well, first we need to start from thinking about what might be happening when the battery remains connected. When the battery remains connected, the voltage is fixed by the battery. We can do anything to this capacitor. We can move the plates away or towards each other. We can add an extra space. We can even place some dielectric inside or take it out. That cannot change the voltage. It's provided by the battery. But if the voltage is constant, but we change the feature of capacitor, that means we change capacitance. That means we change the charge. So in this situation, when battery remains connected, any action on a capacitor might lead to electrons running either way, clockwise, counterclockwise, depending on how we look at it. But if we disconnect the battery, where do electrons run? Nowhere. No matter what you do to it, they just can't run away. That's it. So, not clockwise, not counterclockwise. Step one, it's always instructive to. Now, when we draw a picture which represents the existence of capacitor or something else, we use standard symbols. So this symbol represents a capacitor, represents two parallel plates. There is a special symbol which represents a battery. Very similar, but for the battery, one line is much longer. Longer line always represents a positive potential, positive terminal, and a short, a negative. So this is step one. After step one has been completed, this capacitor has a certain charge, which will be equal to capacitance times the voltage provided by the battery. Now, step two. We disconnect the battery. There is, well, the battery doesn't disappear, but it is not connected anymore. So, in this situation, no matter what is happening to the capacitor, the charge cannot change. Electrons, the number of electrons can't change. All right. I will give you a minute to answer this question. Basically, what do you think about it? And this is how it physically would look like. So we have several capacitors, number one, number two. Now we can connect the capacitors differently to each other. There are two types of connections. When we charge them up, eventually one will be positive plate, or one plate will be positive, one plate will be negative. And if we connect negative and positive together, this is what we call in series. Now, a second possible connection, if we connect negative to negative and positive to positive, that's what we call in parallel. And for each type of a connection, we have certain equations. We talk about it. But first, so in this example, positive to negative, this is how we connect two capacitors, of course, to the battery. And of course, now electrons will run everywhere. Can electrons jump from this plate on this plate? No, cannot. So what can happen? Some electrons, well, if it's positive, this plate has to become positive, which means this plate will be losing electrons. Those electrons will be running through the battery, acting like a pump, and they will be settled on this plate. But now these electrons will repel electrons on this plate, and they will be moving here. So this will become positively charged, negatively, positively, negatively charged. And as we know, if we have parallel plate capacitors, magnitude of the charge on each plate should be the same. And the law of conservation of charge says if 100 of electrons moved from here to here, this plate should have the same charge, but opposite, yeah, so same magnitude. So this simple reasoning tells us if we have several capacitors connected in series, they will have the same charge. This is from the law of conservation of charge. Now, what do they have different? Well, I'm going to check only two capacitors because, okay, no more extra symbols. So that's a battery. the capacitance number 1, the capacitance number 2, the charge number 1, the charge number 2, the potential difference number 1, we call it voltage, should use magnitudes. The potential difference number 2, we call it voltage. So now, this is the voltage provided by the battery. What is the voltage? Potential difference, actual difference between two numbers. One number represents potential here, and the lowest potential always can be set to 0. Second number represents potential here. This is what the battery says. Yeah. This is literally the difference between positive potential and negative potential. Now, for each capacitor, we can write the same equation. Yeah? Q1 should be equal to C1 times delta V1. Q2 should be equal to C2 times delta V2. The equation doesn't depend on anything. It's just a definition of capacitance. But for this specific connection, the charge should be the same. Law of conservation of charge. So, what else can we write? Well, remember, we always make our life easier by making some assumptions. For example, anytime when we use a string, it's massless and unstretchable. Now we use a special assumption about wires, the ideal. So it means electrons can run through a wire without any work done on it. Only work done by the battery. So if a wire is ideal, no work done. No work done. In mathematics, no means what? 0. So if we have a potential here, let's call it, I don't know, V star. Electrons should have been moved, yeah? And the work done should be equal to V plus minus V star. And it has to be equal to 0 because the wire is ideal. And if it's 0, that means the potential doesn't change along a wire. An ideal wire doesn't change potential. So whatever potential I had here at the positive terminal of a battery, exactly the same potential will be everywhere up to this point. Only capacitor may change potential. To what value? Well, to a new value. Let's call it V2 stars. But the potential difference, also called voltage, between these two values, 2 star minus star, is what the voltage across first capacitor equal to. According to the definition of voltage, it's literally the difference between two numbers. But now, there's another voltage across the second capacitor. What should it be equal to? Well, the same reasoning says, because a wire doesn't change potential, potential here, we call it 3 stars, should be equal to 0. So potential difference across the second capacitor should be equal to V2 stars minus V3 stars. And now, if we add them up together, delta V1 plus delta V2 together equal to that original voltage provided by the battery. People say voltage splits across capacitors. So we have 6 here, and we have maybe 2 and 4, or 1 and 5. It depends on actual capacitance. But if we measure or calculate voltage across first capacitor, second, and add them up, we always get the original voltage provided by the battery. That's it. And we will use this fact very soon. So that's the answer. Now we're going to use this fact. So Q equals C1 times delta V1. Same Q equals C2 times delta V2. And delta V1 plus delta V2 equals delta V. And these equations related to what? These equations are related to a situation when we have 2 different capacitors connected to the same battery in series. And now we can ask a very important question. What single capacitor can be used to replace these 2? So it would store exactly the same charge. So we are looking for a substitution. Instead of using 2 or more capacitors, we would like to use just 1. But if we connect it to the same battery, we want it to have the same charge. If such capacitor exists, we call it the equivalent. And the capacitance of that capacitor has a name, the equivalent capacitance for capacitors connected in series. So if that capacitor exists, the equation which relates its capacitance, its charge, and voltage. Yes? Yes, exactly right. We're trying to replace those 2 with only 1 device, because that would save materials, time. Instead of using 2, we want to use only 1, but not like this and not like that. Which one? That's what we're looking for. What should be the capacitance of this equivalent capacitor be equal to? And the answer is this equation tells us that Q over C1 plus Q over C2 should be equal to Q over C. Simple algebra. If we look at this equation, we see we can make it simpler, and if we can make it simpler, we have to make it simpler. How? And this gives us an equation for the equivalent capacitance of a capacitor which is equivalent to several capacitors connected in series. It doesn't matter how many, 2, 5, as long as they are connected in series, we can always replace all of those capacitors with single one. And to calculate the capacitance equivalent to all those, we have to apply this equation, which we just have proved. We proved for 2, but of course, the process works for any number of capacitors as long as they all connected in series. Well, let's briefly talk about easier case. Easier because when we have capacitors connected in parallel, what they definitely have in common is very clear. voltage. When capacitor is connected in parallel to the same battery, okay. The battery makes all plates on the same side have the same potential, which is either positive or negative. See, I need an extra wire. And in parallel, of course, now charge may be different. Actually, I don't have to connect it to this plate. I can connect it directly to the battery. It doesn't make any difference. Still, here, we have the same potential, which is 0. Here, same potential, which is 6. And that makes calculations much more simpler. So potential is the same. Charge, of course, will be different. An equation for the charge, of course, is the same as before. Now we ask the same question. What single capacitor can be used to replace those? Well, what does the word equivalent mean now? It means now that the total charge system stores has to be the same as before. And what is total charge? It has to be charge of the first capacitor plus the charge of the second capacitor, bless you. This is how much charge the whole system, original system, stores. Now what do? Well, we just add them up. This equivalent capacitor connected to the same battery, and the equation which relates charge, capacitance, and voltage still the same. However, it should be equal to charge number 1 plus charge number 2. And now we can simplify this expression by canceling the same voltage. And the result is simple. Now, to calculate the equivalent capacitance, we just have to add the capacitance of each individual capacitor. And it's easily understandable if we look at this model by adding capacitors in parallel, we're basically adding more area, and the expression for capacitance equals constant area. So we double area, we double capacitance, we triple area, we triple capacitance, etc., etc. That's the idea. Well, now we have two equations. One equation tells us how to calculate the equivalent capacitance for capacitors connected in series. Second equation tells us how to calculate the equivalent capacitance for capacitors connected in parallel. We just have to use them correctly. Let's practice. So first we should draw a picture. It helps to make the right choice for the equation we want to use. Oops. C1, C2, C3. We look at the picture and we make a statement. What kind of a connection do we see? And we have only three possible options: in series, in parallel, or neither. It is also an option. We make our choice. Okay, in this situation, in series. And now, because we know what equation should we use, We use it. 1 divided by equivalent capacitance should be equal to 1 over 1 plus 1 over 2 plus 1 over 3. And I use microfarads. My answer will be in microfarads. So what is the common factor? 6, right? So it's going to be 6 plus, bless you, 3 plus 2, right? 6, 3, 3, 2, 2. So 1 over C equals 11 over 6. Now, if you've been thinking about it, if you've been trying to solve it in your head, and I saw it in the past, you could have stopped right here, and that would be wrong, because there has to be one more action which should be done. You have to flip it. We are not looking for 1 over C. We are looking for C over 1. Microfarads. All right. To calculate the charge, we need to know the voltage. Let's say 100 volts. How do we calculate the charge? Well, we have 4 different options. We know that for capacitors connected in series, charge on each capacitor is the same. So Q should be equal to C1 plus delta V1, or C2 times delta V2, or C3 times delta V3. But if the total voltage is 100, we don't know individual voltages, so we have to go for the option number 4. It should be equal to C equivalent times delta V. So 6 over 11 microfarads times 100 volts. That's going to be coulombs. And don't confuse, please, C, which represents capacitance, and C, which represents coulombs. Not the same. Well, in parallel, calculation is even easier. Equivalent equals 1 plus 2 plus 3, 6 microfarads. Now, in parallel, they share the voltage. So Q1 equals C1 times 100, etc., etc. Q2 C2 times 100, Q3 C3 times 100, 100. Q total. Well, we have 2 options to find it. We can add the charges on individual capacitors, or we can calculate C equivalent times 100. Question. I want to ask a question. Maybe it will be the last question I want to ask you today. What do you think in this situation? So as we know, according to a definition, we only have 2 possible connections, or people say wirings, wired up in series, wired up in parallel. And if you look at capacitors 1 and 3, they are definitely connected in parallel. No doubts there. But the question about capacitors 1 and 2 would have been similar question about capacitors 2 and 3. Well, again, we have to compare the definition with the actual wiring. So this is what we call in parallel. This is what we call in series. Our capacitors connected with an extra wire So the answer is what? What should you choose? Is it in parallel? No. Is it in series? No. This is an example when the answer is neither. So we have no, see here, this point has no wires. It's a strict direct connection between one plate and another plate. Why is it important? Because in this situation, all electrons which leave this plate, they have to go to this plate. That's why the charge should be the same. But if we had an extra wire, that's it. Electrons may have an extra path. And that breaks the definition of being in series. So the answer is neither. But what do we do about this situation if we want to calculate the equivalent capacitance of a capacitor which would replace all three? Well, we have to break it into smaller parts. We have to search for a connection which is definitely one or another. And in this situation, we know for sure, definitely, 1 and 3 connected in parallel, which means we always can replace these two capacitors with one, which will be equivalent. So every step which can be made must be made, which means we have to redraw the whole schematic, the whole picture, using the definition of a wiring. When we redraw the picture, we keep parts which we don't change the same, and we change the part which we replace. So this is still the same capacitor number 2. We didn't touch it, we didn't change it. This is still the same battery, 6-volt battery. But we have replaced two capacitors, first and third, with one. The equivalent capacitance of this new capacitor should be equal to what? Because it's parallel, it should be equal to just the sum, which is 1 plus 3, 4 microfarads. But now, after we simplify the circuit, we can look at the new equivalent circuit. And now we can see two capacitors connected in series, which means now we can make another transition. Same battery, and now only one capacitor, which should replace all 3. And how do we calculate the equivalent capacitance of this capacitor? Well, because the connection now in series, we have to use the equation for capacitors connected in series, which means it has to be equal to 1 over 4 plus 1 over 2, 3 over 4. But that is not the capacitance yet. Have to make an extra step. So this is 4/3 microfarads is the equivalent capacitance of this single capacitor, which can replace all 3 capacitors. Actually, what can we do now? We can calculate the charge which that equivalent capacitor would store. (4/3 -6 times 6, 8 times -6 coulombs. And now we have to go back to the original schematic step by step. For example, what do we know? We know that these 2 capacitors should store the same amount of charge because connected in series, they are connected in series. Now, by the way, if I know the charge, I can calculate the voltage for each individual capacitor. The voltage number 2, for example, will be equal to charge over C2, 8 times 10 to the negative 6 over 2 microfarads, 4 volts. So that immediately tells us the voltage 1,3 should be equal to 6 minus 4, 2 volts. But of course, it also should be equal to Q over C13, 8 times 10 to the negative 6 over 4 times 10 to the negative 6, 2 consistent. Good sign. Why did I know? Yes?
So when you're doing the charge of
This? Yeah. 6. All right, so now this voltage is 2 volts. And of course, we can calculate charge on each individual capacitor. By the way, if we add them up, Q1 and Q3, we should get Q2, which is same as Q. And how do we calculate it? Well, Q1 should be equal to C1 times delta V1. Come on. So now I can, what can I do? It should be equal to 1 microfarad times 2 volts times 2 volts, 2 times 10 to 6 coulombs. So this is an example of a very common situation when we have to break down the original circuit into smaller parts. All right. Now, we can relax a little. Yes?
When you found the voltage at why did you subtract it again?
You asking about this?
Yeah.
Because if we add them, we should get 6. Because the battery provides the voltage across the whole system, which splits between the individual capacitors. So voltage 1 plus voltage 2, they together should give total voltage. So I used it backwards because I know total and I know this one. I got that one. Every time, well, this is a relatively simple situation, just 3 capacitors. And you can see that we have a huge number of various connections. Every time when we have a problem like that, we always have more equations than we need. Well, it just, this is just, a fact of this physics. So many connections, so many different approaches. Doesn't really matter which you use, as long as you use it right, you always get the same results. So, first, okay. So, as long as you can see this So what do? I'm shortening it. I could use, of course, a wire, but human flesh is a good conductor anyway. So. All right, it's zeroed. And I can move it. Nothing changes because they still shortened. I can charge it. I just have to connect the battery. 9 volt. That's a 9 volt battery. And what can I do now? I can move the plates closer, further. Doesn't affect at all the voltage, because the voltage is fixed by the battery connected to it. But what is happening if I disconnect the battery? Now we can see the voltage depends on the distance. Why? Well, because when we change the distance, we change capacitance. So no, not that. This. So what happened? First, I charged the capacitor. Step number 1. But then I removed the battery. If I remove the battery, we know the charge should remain constant. Q equals C times delta V. So delta V is equal to Q over C. And when C changes, for example, when C increases, delta V decreases. Now C is related to features of the capacitor. So for example, when distance decreases, C increases. So that's what we saw. The voltage and distance behaves similarly. This is a very typical way of reasoning about capacitors when something happening to them. Now, of course, in physics, we have devices which actually can measure the actual value of a capacitor, capacitance of a capacitor. Simple multimeter, and here we have, well, we call it a decayed capacitor because we can change its capacitance by just flipping the knob. So I can measure the capacitance of this. This is bent and cracked, okay. Well, it should be 10, but of course it's never an exact number. So 11. Now, let's see another one. 11. And what's going to happen if now I connect them in parallel? So I just need 2 wires. So far nothing, because there is no complete connection. But if I connect now a second, it doubled. By adding capacitors in parallel, we're always increasing capacitance. But of course, what's going to happen if we connect them in series? So one wire should go here, second wire should go here. And we need to connect, well, plus to minus, positive to negative. Again, this is the capacitance of a single one. Now 2, a half of that. This is actually a very convenient rule to remember. If you use identical capacitors, identical, in that case, if you place several identical capacitors connected in series, total capacitance equals initial time divided by number of capacitors. But if you use identical capacitors in parallel, so total will be single times the number of individual. That's it. Now, you know everything about capacitors. Now you know everything about capacitance, and now we are done. Thank you. Excuse me. Morning.